Now, the research question we have asked here, what is the long-term spatio-temporal variability of recharge in a semi-arid catchment in South Africa? And we have been looking over a 50-year period. And also, we would like to address what are the relative contributions from these two components at catchment scale, and how has it evolved over time. And the approach we are taking here is an entirely data-driven approach by combining the water table fluctuation methods to estimate recharge at the local wells, and then combine that with a machine learning modeling framework. This is our study area. This is Hout Sand catchment, and you will be hearing more about that in later presentations tomorrow. And as you can see here, as listed here, is a tributary to Limpopo River. It has a sizable size, 7,700 square kilometers. And groundwater resources have traditionally been the water source in this area, are mostly for irrigation. But due to increase in irrigation and also increase in population, more stress are imposing on the groundwater resources. And that is why one of the motivations for us to look into this. Just briefly about the geology, we are dividing it into two categories. The black area here, this is the gneiss area, and the yellow one, this is the alluvial deposits next to the river system. And then here are collected as many observations of groundwater levels as we can retrieve for this 50-year period. Just to summarize, the water table fluctuation methods is listed here, and in a way it's very simple, because when you see an increase in water table, that is presumably due to recharge coming in, and then you need to normalize with a specific yield. And you also need to take into consideration the lateral drainage and also if pumping, if that is the case. Now, in our analysis, we have neglecting the impact of pumping. And this is a typical groundwater hydrograph where you see during the wet season, you see increase in the water table, and during the dry season, then you see a slow decline. And from this decline here, we are then able to estimate the drainage constant, and by estimating or assuming a specific yield, then we can then at the individual boreholes estimate recharge. At the lower graph, you can see all the well data we have collected from a total of 97 groundwater wells over this period. And what is characteristic here is that at certain times there's only few wells available. Later times we may have observations for more. And then here it may decline again when we are coming to later times. So there is a variability in the temporal amount of data we have available, and also it changes. Some wells are active at some time, others at other times. So this is where the machine learning modeling framework comes into play. In order to apply the water table fluctuation method, we have to assume values for the specific yield, and this is what is listed here for the alluvial 0.075, for the hard rock 0.71. And of course, that is subject to uncertainty. The second assumption we have made, this is the aerial extent of the alluvial deposits, according to this figure here. And then we have also assumed that the vertical extent of the alluvial is 10 meters and subject to this variation. Now, having done that, then we can estimate the recharge on a mean level, 39 millimeters per year. And also, we can divide it into focused recharge. It has a mean level, mean value of 106 with a large variation. And likewise, we can also estimate the diffuse recharge which we have come to 29 millimeters per year, and also subject to some variation, depending on which year we are looking into. Now having, let's see, just go back. Having done that, when we have been able to calculate 1,500 annual recharge estimates for a hydrological year. And this is then the basis for introducing into the machine learning model. And by this, we are able to generate the annual recharge map at 100-meter resolution for a 50-year period. And then we train the model according to 15 covariates, divided into these categories here and listed over here. So we have a geological covariate, we have a water body relation, mostly distance to the river system, topographical input, and also hydroclimate input. And they are all listed here. I'll not go into details, but we use these 15 covariates in order to train the machine learning model. Having done that, then we are able to compute the long-term average of recharge for our focus area. And this is shown here on the left. And as listed to the right, the catchment average has been computed to 46 millimeters per year, or around 10% of the mean annual precipitation. However, it's subject to a large spatial variation, as you can see here. At places it's 6, at other places it's extremely large due to the impact of focus recharge. And also shown on the map here, you can see that the highest recharge occur along the river network and the dikes, and the highest at the intersection. Although we can also compute the interannual difference, and that is shown to the right here. 91, we have little average recharge. Year 90, that's wrong, it should be 99. The mean recharge is considerably higher. We have also computed how it varies over time, and this is the recharge, how it varies over time, and we have seen a significant decline in the recharge over time. Even though the precipitation has remained fairly stable as far as the mean precipitation is concerned, however, we have also analyzed that we can see an intensity of daily rainfall, number of wet days, and also duration of dry days. Finally, this is then the division into the focus recharge. This is the bottom line here, and the diffuse recharge. And we can see at catchment scale, then the mean diffuse recharge is 37 millimeter per year. The focus is 9 millimeter per year. We have also seen that over the year there has been a significant or statistical significant trend, negative trend in both components. However, when relating them to each other, then we see that the proportion of focus recharge in relation to the total recharge has increased over time. The mean focus recharge is about 20%, and it occurs over according to 20% of the entire recharge, and it occurs over 20% of the 12% of the catchment area. And here are some few conclusions, and yeah, you can read them. Okay, 1 minute? Okay. The absolute recharge values we have obtained is higher than other studies have shown. And there can be several reasons for that. The water table, the results of the water table fluctuation method is extremely sensitive to the specific values that we have, that one specified. And we have taken literature values and also estimated the range. So it's subject to uncertainties. However, also other studies reported in the literature also are subject to uncertainties. So I think that we are still struggling a bit with estimating recharge at catchment scale in semi-arid regions. Now, finally, I want to say that using a machine learning algorithm, as we have done there, then we can overcome the problem of scatter data in space and in time. And a machine learning model is extremely fast in computational time, much faster than running integrated numerical models. Thank you very much.
Thank you. I think you can see that we are a little bit bumpy. So, any questions, colleagues? If there's a question from the floor, we really appreciate it. That's a very interesting presentation. I wish we got it before we even finalize our hydrogeological map series for Polokwane area. But anyway, any question? Okay, there's a hand there. Another one? Second one there. So two hands, fine. Can come through.
All right. Thank you very much for the opportunity. My question is on the training of the machine learning algorithm. Like, how long does it take for you to say that this algorithm have actually managed to reach to the point where we can actually say we are now generating accurate models that are close to accurate? Thank
you. Based on this machine learning method, and it's subject to uncertainties. And the important issue here that it is entirely data-driven. So we are estimating the recharge at the well scale, but depending on which specific yield we are assuming, if you double the specific yield, you get double recharge. So very simple. But I think it can, I'm not saying here that we have come up with the perfect solution, but I think it can complement other studies, and at least this is a methodology that can give some insight into the recharge phenomena. And given the issue that we are always confronted with spatial variability in the availability of wells, and also temporal heterogeneity. So this method can sort of do a spatial and temporal interpolation and give some insight into the recharge phenomena.
Okay, thank you very much. I have two questions. Number one is, in your results, you indicated that recharge was declining.
Sorry, maybe just stand up. You want to see you?
Yeah.
Okay, thank you.
I'm not tall enough, even if I stand. Okay, so I was saying I have two questions. One, in your results, you mentioned that the recharge was declining despite precipitation being stable.
Despite that the annual precipitation is stable.
Yes.
But the intensification of the rainfall has changed. Longer dry periods, more intense daily rainfall. And that can be a cause for this.
Yeah, so my interest was on the policy implication now. Is there any policy implication that your results could have? What could you advise policymakers in terms of maybe land use planning, for example, to encourage recharge or something? I just want to get your views on that one, the policy implication of that particular result. The second question is, in the methodology, you mentioned that there were certain values that were assumed. I think it was specific yield, if I'm not mistaken. How were the figures arrived at? What was the basis of the assumption? How did you make sure that your assumption is not affecting the model? Or how did you validate it? Thank you.
Well, first you need to train the model, and I didn't present that. So you need to train the machine learning model on the basis of the available data. And we got an excellent, very good correlation And the most important parameter here, that was the distance to the river, the distance to the dike system, which also are incorporated here. Not only divided, we had a division into alluvial and gneiss, we also incorporated the distance to the dominant dike system, which also are present here. So these are the most important issues. And then further down the list then comes the precipitation, and we also had a range of different climate indices, which we also incorporated into this machine learning concept. I'm not here to claim that now we have the perfect results. I'm here to claim that this technology, this methodology, can add to a further knowledge of the research phenomena, how it varies in space, and how it also varies with time.